good morning. I think in today's class we continue with where we were yesterday, namely the theory of rocket propulsion. You know, in order to set pace and just make sure we are on the right track, I will go through one or two slides which will illustrate where we were yesterday, and we will also illustrate that not only rockets do something in space wherein we eject momentum, in nature itself we find lot of things which make use of the same principle. For having said that, let us briefly go through some of the things. You know, we told ourselves that rockets are used to launch satellites, maybe objects in space. We talked in terms of circular orbits, we talked in terms of geosynchronous orbits, polar orbits, sun synchronous orbits and retrograde orbits, different orbits. We also talked in terms of elliptical orbits, and we said elliptical orbit is one wherein you have two foci. This is, let us say, the earth, and this is the spacecraft going round. We defined something known as eccentricity, which was the distance between the two foci and the major axis, which is 2a over here. We also said for an elliptical orbit we could have an inclination, even a circular orbit could have an inclination, and the inclination is between the equatorial plane and the plane of the orbit. I wanted to make it clear because we defined one orbit known as a Molniya orbit, and we told ourselves in the northern hemisphere, a country like Russia or something, wherein the satellite has to stay in the orbit above the northern hemisphere for a longer time. We have highly elliptical orbits wherein the apogee is at a distance of something like almost like 60,000 to 70,000 kilometers, and the perigee is quite small, of the order of 6,000 kilometers. With the result, what we told ourselves, yes, I have the earth over here, this is the northern hemisphere, it is in the northern hemisphere for a very long time, something like 11 hours it is in this period and only 1 hour here, so that a country in the north can view the satellite for a longer time. This Molniya orbit is particularly important because it is something which was developed in Russia, and we told ourselves this is the apogee, which is of the order of 70,000 kilometers. We told ourselves this is perigee, and the inclination of this orbit we told ourselves is something like 63.4 degrees. Having said that, let us go forward. We also talked in terms of the rocket principle, and we told ourselves if when we had the sled and we had these two boys who were throwing stones together, we got the net velocity of the sled was something like the mass of the stones thrown divided by the total mass into the velocity with which the stones were thrown. The important thing here is when we are looking at the sled which is moving, we are talking with the inertial frame in mind. I look at the sled, I am standing here, namely there was this sled here, there was this boy, you know, I am observing it from the inertial frame of reference and writing the momentum conservation equation. When the two stones are thrown independent of each other, that means one after the other, we got a higher value of velocity because we got in the denominator 2m by m was what we got when the stones were thrown simultaneously. Now we got m by m plus m over m minus m. Since m minus m, capital M minus small m is less than small m, I get an increased velocity. And so if I have a series of stones thrown one after the other, well, I can get a higher velocity than both the stones thrown together. The question is, why is it? Because when the net mass is decreasing and I throw the same and I throw one stone, I accelerate a lesser mass and I get a better one. Therefore, we find that when I throw one after the other, I do not have something like a stone being thrown, in which case I have the net velocity is equal to u plus at, but since I am accelerating or I am sort of forcing a mass which is lesser in one, I get much better velocity. This is what we said. Having said that, let us go back and look at some examples. I chose some examples, you know, this is from the National Geographical magazine. What is shown here is something known as a squid. This is known as a squid. Squid is something like a large fish, something like 10 meters long, is what it is. It is found off the coast of Japan, maybe New Zealand. It periodically visits these coastal areas, and it is an endangered species, and it propels something like the rocket principle itself. What it does is, let us look at the parts of this particular squid what is available here. This is something known as a mantle. There is something like a funnel here, and what it does is, let us go to the next one. See, this is a squid which is caught, which was picked up from off the coast of New Zealand, and you see the length compared to this man, it is something like 10 meters long. Let us go to the principle of it. It is something like a funnel here. What it does to move itself is, it opens its snout, or it opens this part of the funnel here, maybe gulps in water. As it gulps in water, it gulps in some sand, maybe eggs, maybe small fish, whatever it is, it gulps in here. Then it closes the funnel over here, it closes its gate or the mouth as it were, and then it through its muscles it contracts itself such that it builds some pressure of water within this mouth, what is available here, and then when it wants to move, it just opens the gate again and squirts out the water in this direction, and when it squirts out the water in this direction, it moves in this direction. It keeps on squirting the water and it propels itself. Therefore, what it does, it moves by shooting water out from its funnel, and whenever it wants to move, it expels water, waste eggs and all that, and that is how it moves. It is very similar to a rocket thing. It collects water, pressurizes the water, releases the water gradually, and it moves out. And the type of velocity what it gets, if you really see, is it expands it, pressurizes to around 0.4 times the atmosphere, and then in one squirt, once when it pushes out, it is able to leap something like 50 meters and gets a velocity of something like 2.5 kilometers per hour. It is quite phenomenal. That is something in the water which is viscous itself. It is able to go at that speed because of the gradual or the release of water, pressurized water from its mouth. If you really see, this is where I show the funnel again. It opens its mouth, water enters, it contracts itself, and then it opens it, it closes the gate, compresses it, releases the pressure, then the water and whatever is available, let me get it, is squirted out and it moves. And this is the principle of what we call as the giant squid. In fact, in US we had projects known as Squid project. Squid project was after this because that is again a rocket project, and it was named after this particular a creature which lives in the sea. In what way is it different from a fish, let us say? A fish, what it does is, it has fins, it displaces the water. That means it slowly displaces the water. Like I go on a boat, let us say, I am sitting in the boat, I have a oar, with the oar I displace water. I displace some water, but the mass of water displaced is large, but the velocity I give is small. In these cases, what does the squid do? It takes the amount of water is small, but it pushes it at high velocity and it is able to do a much better job. I think this is all what I wanted to tell, and I just illustrate this. If I have a water rocket, if I want to make one, all what I do is I take one of these maybe bottles like this, maybe I invert it, I put a constraint here, I pressurize it with gas over here, and then when I pressurize it, water squirts out and this can go up. And this is precisely the principle by which maybe the squid propels itself, and this is where I show maybe a rocket here, maybe water is here, high pressure gas here, water getting squirted out and the rocket moving up. The principle of any rocket is exactly the same, only thing is that you need higher velocities, therefore you put more enthalpy into the system which expands over here. The thing which is expands has higher enthalpy, therefore I get higher velocity. Maybe you need something which will increase the velocity still further, and that is what we are going to learn in this particular course. Having said that, I came across some other example. I was teaching at IISc a course on propulsion, and at that time one of the teachers that told me that there is one insect which is available in nature which uses the rocket principle. I tried to get some information on this, and this is what is known as a bombardier beetle. Beetle, in Tamil we say vandu, or in Malayalam it is known as nandu and all that. What does it really do? It is a harmless creature, it goes round and all that, and whenever it comes we take a cardboard, we take it and throw it out, that is all what we do. This bombardier beetle is one wherein it is a harmless creature, but being harmless, these ants and all go and sting its leg, therefore it is always in a state of alertness. But nature has given it some features. Let us see what exactly it is. It has something like 2 stomachs. After 2 stomachs there is another receptacle here, a third stomach, and in one of these stomachs what it generates is it secretes hydrogen peroxide. In the second stomach it secretes something known as hydroquinone, which is a fuel. Hydrogen peroxide is an oxidizer, hydroquinone is a fuel. The oxidizer hydrogen peroxide and hydroquinone, when it is chased or when it is bitten by ants, it immediately squirts it into the third stomach, wherein both the things react, generate hot gases, and these hot gases it sort of squirts out. And when it squirts out, you have a jet coming over here, maybe it kills this thing and it also moves forward. Let us see the principle again. Here I show the 2 stomachs, in one hydrogen peroxide, in the other hydroquinone. They are secreted here. This has a lining of mucus which acts as a catalyst. It promotes the reaction, and whenever it wants to move it just squirts it out, something very similar to what we say is a liquid propellant rocket. What does a liquid propellant rocket do? We are still to get into it. You have a fuel tank, you have an oxidizer tank, you pump the fuel and oxidizer into it, you ignite it and you push the gases out. So does this small insect which is available in nature. I think we should look at nature to understand many of the things what we are studying. Everything is there, maybe we have to be more observant. Having said that, let us get into some details, but having said this, I thought I will also illustrate, because we told ourselves whenever a satellite is there in space in geostationary orbit, sometimes we have to push it out, and therefore any satellite has something like 16 rockets which are there at the edges of this, and these are used for correcting the attitude, maybe station keeping of the satellite, and whenever the lifetime of the rocket is over, we fire some of these things such that we remove it from the geostationary orbit and push it into deep space, and this is an INSAT satellite. I think this is all I want to illustrate at this point of time. I will come back to the slides a little later. Let us, with this background, ask ourselves, how do I develop the theory of rocket, or what we call as the rocket equation. Let us get into this. What do we mean by rocket equation? See, it is so simple, but you will be surprised to know that the rocket equation was developed quite late, only in the year 1903, and that also by a Russian school teacher by name Tsiolkovsky. Now let us see how this, and therefore this rocket equation which describes the propulsion of a rocket is also known as Tsiolkovsky's equation. Let us derive this. Let us go back. We will follow the same procedure what we adopted while finding out the velocity gained by the sled, these 2 boys standing on it, throwing one stone after the other, but we will make some simplifying assumptions. Let us assume I have a rocket. For the present, we will assume rocket has a shape something like this. It need not really be this shape, maybe as we evolve, maybe you all will come out with better configurations of rockets. Let us say at time t, it is moving with a velocity, let us say v. Let its mass at time t be capital M. After a small time, t plus a small time, let us say delta t, delta tau, a small time period, delta tau seconds, it is again now what does it do? It is moving forward, and then during this small time a small mass is coming out, it is ejecting matter. Therefore, it has lost a mass, let us say delta m during this period, and let us say it is also ejecting mass at the velocity. Why should I put an arrow? We will make it even more general. It is ejecting mass at some velocity Vj. I do not know whether mass is moving upward or downward. I just presume that velocity Vj, some mass has left the rocket, and therefore, the final mass of this rocket is going to be m minus delta m over here, right. Let us presume that the velocity of the rocket at time t plus delta tau seconds, this is at time t, this is at time t plus delta tau, is v plus, let us say del or small delta v. Let me repeat the assumptions again. A rocket is flying with a mass m at a velocity v at time t. How does it fly? It keeps on releasing mass at a velocity Vj, and during a small time delta tau, it releases a mass delta m with a velocity Vj, and therefore, because of this the velocity increases, because we presume, let us find out whether it really increases or not. We think that the velocity would have increased from the original value of v to v plus delta v, but since it has lost a mass delta m, the final mass of the rocket is m minus delta m. Okay, this is the problem. Now, we talk in terms of inertial frame of reference. Therefore, I am here, I am watching the fun, I watch it, I am in the inertial frame of reference, I am looking at the velocity rocket go with a velocity v, and then after a time delta tau I am looking at it going with a velocity v plus delta v. Now, I do the momentum balance in the inertial frame of reference. What is it I get? The initial momentum of the rocket is equal to what? Yes, it is mass into velocity, is that right? Now, what is the final momentum of this rocket as I am seeing from here? I have m minus delta m into v plus dv plus, you also find that delta m has gone out. Therefore, I have delta m, and what is the velocity? How do I see it? The rocket is flying at v plus delta v plus Vj over here, that is the velocity of the stone, the relative velocity Vj plus v plus delta v. This is how we wrote the equation for the sled, right. Therefore, we write exactly the same way, and therefore, we find this is the initial momentum. In that case, the sled was stationary, initial momentum was 0. In this case, this is the rocket plus whatever is left behind. Therefore, for this system, this is the momentum equation, right. If it is all right, let's simplify it. What do we get? Therefore, mv is equal to mv minus delta m into v, then I get plus m into delta v minus delta m into delta v. Now, from this set of equations I get plus, from this term I get delta m into Vj plus delta m into, see I should have written here small delta, right, that is the value which I said, because we should have been independent, because I want to reserve the capital delta for something else. Therefore, delta m into delta v, and now I find that this delta m delta v cancels, mv cancels. Therefore, I am left with, I can write delta V is equal to, yes, what will I get? Let us write it. Delta V will be equal to minus plus delta M. Are the signs all right? Please check it. Delta M into V divided by, yes, is it all right? See, what did I get from this equation? Let us write it again. We get minus delta M V plus M delta V is equal to 0, and therefore, delta V is equal to delta M into V divided by capital M. Just see if there is any error in this equation. Can I go forward? Which one? Let me write, let us derive it. Yeah. See, MV is equal to MV plus M delta V minus delta MV minus delta M into delta V plus delta M into Vj plus delta M into dV. I get this and this term cancels. This one term is missing. Hey, how can I get so many terms? Let's see, we have made some mistake somewhere. MV is equal to MV plus delta MV, yes, and I have M delta V. I have 4 terms. That means I have what happened to a term here? Delta M Vj plus delta M plus I should have got, I have forgotten this, namely delta MV, and this delta MV and this delta MV should have cancelled. See, when I expanded this out, I have delta MVj plus delta MV plus delta M delta V. Now, thank you for pointing it out. See, I have 3 velocities here. I have Vj, V and delta V. Therefore, I should have got delta MVj plus delta M delta V, which I wrote. I had skipped this portion, and now I get delta M into V over here. Is it all right? Therefore, what is it you are telling? Let us write it out. Therefore, M delta V plus delta M Vj is equal to 0. Therefore, we get delta V is equal to minus Vj into delta M by M, or let us say delta M, we used the capital delta M here. Okay. Now we want to solve this equation. How do I solve this equation? I get delta M. What is the value of delta M? Let us assume that the mass which gets exhausted from the nozzle is something you are constantly pushing out mass at the rate, let us say, m dot. Therefore, the value of delta M should be equal to m dot into the small time, what I said here, delta tau, okay. You know, the rate at which mass is leaving the nozzle is m dot over a small time delta tau, it is equal to m dot delta tau. And what should be the value of the capital M? Capital M must be equal to the initial mass of the rocket at time t is equal to 0 minus m dot. We are telling that is the mass of the rocket at time t, this is equal to m dot into t. In other words, at time t is equal to 0, the rocket had a mass, initial mass, it continues to eject mass at the rate m dot, constant value, and therefore at time t its value m is equal to mi minus m dot into t, right. Now please keep checking, and therefore now I can erase this part. and now I can write the value of delta V is equal to minus Vj into delta m is equal to m dot into delta tau divided by mi minus m dot into t. I want to integrate this equation, and if I have to integrate this equation, I get this is equal to I have to integrate with respect to time. I have to integrate this equation from the time t 0 or t is equal to 0, let us say, to the final time at which I get a total velocity increment of delta V is equal to Vj into, now I get the value of m dot, I call it as dt into mi minus m dot t. Of course, I had a negative sign somewhere, but you know one thing I have missed somewhere. What is it I have missed? I think that is very important. I think one of you must find out. I should not get this negative sign here, and what is the mistake we have committed? What did I write here? I told you mass at any time is equal to mi minus m dot t. Therefore, how would I look at the value of delta m? Delta m is equal to what? I think this is important, you know. Let me put that on this equation. I do not want to rub this out. Let me again put this here. I think this is important, is equal to mi minus m dot into time t. Therefore, what is the value of delta m is equal to, over a small period delta tau, what is the value, is equal to minus m dot into delta tau. That means, if I consider, I called it as delta tau in a short period. Therefore, what is this minus sign? Minus sign shows that the mass has left the system, and therefore, when I substitute the value of delta m, I should have substituted minus m dot delta tau. That means, this should have been a negative sign, and this negative sign and this negative sign would have given me a positive sign, and the expression should have been plus Vj. Please let us go back, check it again. Now, this is important, you know, because the frame of reference we must be clear, we must know what is leaving, what is gaining. Therefore, what is it we have done? We took the momentum equation, and when we took the momentum equation, we balanced mv with m minus delta m into v plus delta v plus delta m into Vj plus v plus delta v, and then we got an expression which gave us delta v was equal to minus Vj into delta m divided by m, and we find delta m is equal to minus of this particular expression, and therefore, we got it as Vj m dot del d tau into mi minus m dot t. Let us ensure this is very absolutely clear, because this is the basis of all the Tsiolkovsky's equation or rocket equation. We must be absolutely clear about it. I want to integrate this equation from the start of the rocket at 0 velocity to the final value at Tf, and therefore, I say I want to integrate it Vj from this to this, and what is the expression I get now is equal to Vj. Let us assume that the velocity with which it is leaving is a constant Vj into, now when I do this I get logarithm of, now I get another negative sign, that is 1 over m dot cancels, and therefore, I get ln of mi minus m dot t going from 0 to the final value of t, and of course, I get a negative sign because this is over here. Is it all right? Please check it. Anything wrong on the board or anything? Can I proceed? Okay. Now I'll ask you, what is the value of mass at time t is equal to 0? The mass is mi, at t is equal to 0, the mass is equal to mi, which is what we specify. At time t is equal to t, the mass is equal to mi minus m dot into the final value of time, which is Tf I call it, which I call as the final mass of the rocket. And therefore, what is this value? Delta V is equal to Vj into ln of minus Vj is there, ln of I get Mf by Mi initial mass, or if I want to take the negative sign into the logarithm over here, I get it as Vj ln of initial mass by final mass, which is the incremental velocity which I get from a rocket, or the velocity what I get from a rocket, and this is what is known as the rocket equation. All what the rocket equation tells is, when I burn a quantity between the initial value and the final value, and I am exhausting it out at a constant velocity Vj, the final velocity is equal to the velocity with which I am ejecting matter out into logarithm of the initial mass to the final mass, and this is what we call as the rocket equation. And it called for this Russian school teacher to come and derive it, and he said, with using this we can go wherever we want, we can go into interplanetary missions, because all what we want is, we want a jet velocity and the mass should keep getting depleted, and this is what is the theory of rocket propulsion, or which we say is the rocket equation. Is it okay? Can I repeat it to some extent? See, because this being the basis, and why I keep harping on this is, there are some limitations we have with the existing rockets, and if we want to go any further to make better ones, we have to look at the way things work, namely we said the jet velocity, or the velocity with which mass is being removed, into ln of the initial mass divided by the final mass, and the value of final mass of a rocket to the initial mass of the rocket is also called as the mass ratio of a rocket. When I say this is the velocity which a rocket gives, I did not consider the gravitational forces, I did not consider drag and all that. Therefore, delta V is also spoken of, or it should be called as ideal velocity increment. Now, let us go back and see what did we learn in the earlier 5 or 6 classes. What did we tell ourselves? To be able to put a satellite or an object in space, I have to overcome the potential energy, I have to give the orbital velocity, and the total velocity we derived the expression by the term, if I can write it correctly, let us say Vt is equal to under root G me by r for the case of the earth, Re plus 2h divided by Re plus h, so many meters per second is the velocity what was required. Now, if I have a rocket and on top of this I put whatever I want to launch, I give it a velocity, I can put it in orbit, and but we told ourselves I need a velocity of the order of, when we did some homework problems, we found we need something like 10 to 12 kilometers per second. Therefore, what is required in order to give high velocities? See, you have to have mass ratios which are that means the ratio of the initial mass to the final mass must be a good number. That means the difference between the initial and final must be large, and also the Vj must be a large value. That means the jet velocity becomes a controlling parameter, and a higher the controlling parameter, higher this jet velocity, you can have a higher delta V what you require in missions, and in addition you need a large difference in this. Therefore, the figure of merit of a rocket, if somebody were to ask us, we must say, well, one is the jet velocity, the other is something related to the masses. Therefore, let us go back and look at this term, because this is fairly clear to us. What am I telling? Let us again put a figure across over here. Supposing I were to exhaust at some jet velocity, and I can get as high a value. See, apparently you cannot get the speed of light, you cannot get more than some amount, but I have some limitations. I will come back to these limitations. Plus, in addition, I am talking in terms of Mi by Mf should be a large number. Let us just examine this number before I come back and see how best I can make a rocket, because as of today you cannot get more than something like 3000 to 5000 meters per second as jet velocity. We will find out what limitations are there, but let us first examine this and we come back to this. Let us therefore go forward. Can I say, yes, the rocket equation is understood and we are in a position to now go back and analyze what are the parameters which are the drawbacks? Let us go for this. Let us therefore write the ideal velocity increment is equal to jet velocity into ln of the initial mass to the final mass of the rocket. What does the initial mass of the rocket consist of? Anything you take will have something like the useful part of it. What is a useful part of a rocket? The object which is going round and round, that is the useful part of the rocket, which is we call as payload, correct. Then the second one what we have is the structure of the rocket. That means it must have some metal and all that, which is all there, the structural part of it. It will have some inert something to glue something, to contain something, that we call it a structural mass. Let us say structure. Plus it should also have some fuel, and we said fuel is used for propelling and it is known as propellant. Therefore, we have something known as MP, which we call as propellant. That means a rocket initial mass or the mass of a rocket comprises of the payload, the structure plus the propellant, and we say Mi is equal to Mu plus the structural mass plus the fuel or the propellant, right. This is the initial mass. When the rocket has done its job, what must be the final mass of the rocket now? It has done its job. That means all the propellant has burnt out. Therefore, the final mass will be the useful one plus the structure and all will still remain, because it is still there. But we will come back and see whether we can also remove the structure and throw it out, but otherwise the structure will remain. Therefore, the initial mass is Mu plus Ms plus Mp, the final mass is Mu plus Ms over here. Now, let us go back and analyze the masses. Let's erase this out. Vj ln of Mu plus Ms plus Mp initial mass Now, we will, instead of working with these kilograms of mass, let us put it in terms of non-dimensional or mass fraction, and let us say I call the useful mass of a rocket mu divided by the total initial mass, namely mu plus ms plus mp as equal to alpha. This is the initial mass of the rocket. I non-dimensionalize the payload mass. Similarly, I non-dimensionalize the structural mass by this particular one, which is the initial mass as beta, and similarly I take the payload, I am sorry, the propellant divided by the initial mass, which is equal to mu plus ms plus mp as equal to gamma, and therefore I get this equation getting simplified into delta V is equal to Vj ln of what will happen, mu I divide mu by mu plus ms plus mp, I get alpha plus beta plus gamma divided by alpha plus beta, and what is the value of alpha plus beta plus gamma equal to? One exactly, and therefore I get delta V. In fact, I could have just divided it and got this, but I thought we should go through this procedure, Vj ln of into 1 plus alpha plus beta. That means that ideal velocity increment as a function of jet velocity is ln of 1 by the payload mass fraction, useful fraction, plus the structural fraction. Now, what is it what we want to do in a rocket? We want to have as much payload as possible. Maybe we would like the useful mass to be high. Let us say what is the fraction of the useful mass I get. Therefore, from this expression I get 1 over alpha plus beta is equal to E. I take exponential on both the sides, the long term vanishes, e to the power delta V by Vj, or rather I get alpha plus beta is equal to, no, I should have just got e to the power, right. 1 over alpha plus beta is equal to e to the power delta V by Vj. Therefore, alpha plus beta is equal to e to the power minus delta V by Vj. Okay. Now, let us examine under what conditions will I get the value of the usefulness of the rocket will therefore be equal to e to the power minus delta V by Vj minus beta, and let us try to plot it out. Let us try to plot it out for different values of Vj for different velocity increments, because we already told ourselves we need this to be of the order of 10 kilometers per second. There might be some strictures on the jet velocity, it is of the order of 3000 to 5000 meters per second. What are the values of payload fraction what we get? Let us just plot it out and see. I will show it through slides a little later, but let us try to see what is the dependence we get. Alpha as a function of delta V by Vj for different values of beta, we find that the values keeps decreasing as delta V increases, because it is minus over there, it keeps falling, and generally this value might be around 0.4, and this keeps falling drastically, and in the operable regions these values may be around 0.1 to 0.2 or something, and as beta increases you find it is minus beta. Therefore, as beta increases it keeps falling. I have still not put any numbers here because we do not know what is the range of beta, but generally beta should be around, let us say 0.1 as beta increases to around 0.12, around 0.15. That means the payload fraction will keep decreasing as the structural mass increases. If I can have a high value of Vj, then I can get a higher value of the payload fraction, or if I have a rocket or a object which requires more ideal velocity, then I get a lower value of payload. We are just looking at the rocket equation and trying to draw some conclusions from it. All what we conclude is, if I want to put a payload of higher mass, then I need a structure which must be very light. I must have a very light structure, or rather my Vj must be large such that I am over here and I get a higher value. Or if I can have a rocket which does not have to go very far away, it is orbiting nearby, then I can carry a higher mass. Otherwise, subsequently I have to do some tricks to put it up. Well, this is all about the rocket equation and we are trying to look at it. Maybe I will have to revisit this in some different way. But then the problem is, see, we are still talking of 10 to 12 kilometers per second, which is the velocity what I require. We called it as Vt, right. This is what we said as velocity which is required to orbit. Vt is of the order of 10 to 12 kilometers per second. But then to get these things, if I have a single rocket, I may not be able to get that, because I have a definite mass of the structure, I have a limitation on Vj, and therefore to be able to launch a payload into orbit using a single rocket is difficult. I use the word difficult because it still, I do not know whether it is impossible. So far it has been impossible, but the quest for the rocket engineer is to make a single rocket do the job. But how do you make multiple rockets do the job? Let us examine this point. Let us say instead of having a single rocket, I make two rockets. I put a rocket over here and on top of it I put another rocket. This is my first rocket, this is my second rocket. Now the first rocket gives me a value of the ideal velocity delta V1. The second rocket already has a delta V1 when it starts functioning. It gives me a value of velocity delta V2, and the total velocity of this composite one after the other, that is a two stage rocket, gives me a delta V equal to delta V1 plus delta V2. And therefore, by putting one rocket after the other, that means one stage of the rocket after the other stage, you get what we call as multi-stage rockets. And most of the rockets which we will be seeing in the slides today would be all multi-stage. That means you want a velocity increment of something like 10 kilometers, maybe the first one could give you 2, the second one could give you 4, the third one could give you still higher, and therefore you keep on adding, and this is what we say as multi-stage rockets. And therefore we tell ourselves, using the rocket equation, I now say I have known as multi-stage rockets, which can give me whatever be the velocity what I want. And how do I get it? I have delta V is equal to Vj ln of maybe the initial mass to the burnout mass of the first one, plus now I have Vj maybe for the first one, maybe I have for the second one, logarithm of the initial mass of the second one plus the burnt out mass of the second one, plus and so on, I get the final ideal velocity. Maybe we should try to analyze this in some detail, but I think all what I am telling is we are talking in terms of staging, or we use rockets as stages. You all would have said, yeah, something is the base stage, then on top of it we have the first stage, then the second stage, and so on, and this is what we say. Let us take an example. Let us talk in terms of our own GSLV vehicle, which is very much in the news. We tell ourselves, yes, this rocket consists of a core, it consists of something attached to it at 4 things over here, then it consists of the second stage and the third stage, and on top of the third stage sits the satellite. Therefore, you have the first stage, second stage, third stage. This gives you delta V1, delta V2, delta V3, which gives you the velocity to put it into orbit. Therefore, we talk in terms of staging. Staging means one after the other. But what about these things and why are they required? Maybe we need to understand a little bit more. What is it we have done? We have put one stage on this, the other stage on this, and you have the payload, therefore you have increased the mass. When you have increased the mass and you want this, it should generate sufficient force for it to go. But this fellow may not be able to generate that force. Therefore, you need additional rockets so that the force or the thrust is able to take off, and that is why we put rockets together, and this is known as clustering. Why do we need clustering of rockets? To give you sufficient force. Maybe to be able to derive something about force, I think I will divert a little bit and look at what are the what do we mean by force, what do we mean by thrust, are there any more definitions which we need to keep in mind to understand this clustering of rockets, staging of rockets. Let us just put things, well, let us just summarize what we have learned so far. We told ourselves a rocket gives you delta V. How does it give you delta V? Because of change of momentum, right? And that is because, why did I say change of momentum? I am standing here, I am watching the momentum change, I wrote the momentum change and I found out the value of delta V. What is the change of momentum known as? It is known as impulse I. What is the unit of impulse? Same as momentum, kilogram meter per second, but kilogram meter per second can also be written as kilogram meter per second square into second, which is same as Newton second. Therefore, I can write the impulse as equal to Newton second, right. Now, therefore, the impulse in Newton second is what gives delta V. Therefore, what is the force with which the rocket is pushed up? What is the force with which the rocket is pushed up? Rate of change of momentum, that means d by dt of mv or d by dt of I. That means it is equal to d by dt, that is I get so much force, which is equal to d by dt of mv, which is equal to mass of the thing which is going into V, which is equal to m dot into V. And therefore, I can also write the force is equal to m dot V, or compared to momentum which is equal to mv, I write force is equal to m dot V, and this is the force with which I am pushing the rocket. There is a limit to the mass which can be released, m dot which can be released, and therefore, I allow more masses to be going through this at a high velocity, and I am able to give a force. That means I need a larger force to push it, and that is why I allow these things. Sometimes what we do is, we have a booster rocket, we put two attachments over here. What are these attachments? They are like straps. I strap something onto it, I attach two straps, and therefore, the side rockets are also known as strap-ons. Let me take one or two examples, maybe I will show it through slides when we meet in the next class, but to be able to just conclude at this point of time, all of what I would like to say is, we derived the rocket equation through the change of momentum, right. We looked at the inertial frame of reference, watched the rocket go up, and we found out what is the ideal velocity. We also told ourselves there are some creatures in universe which also make use of the rocket principle. Then we found out that the structure plays an important role just as much as the jet velocity plays a role. Then we found out to be able to get a high value of delta V, we have to operate in stages, and to be able to take off, we need some additional side rockets, which are known as clustering or strap-ons. Thank you. I think we will continue with it in the next class, right.